Okay, example 7, 110-pound box is on a 24-degree ramp. Find the component of the force that's parallel to the ramp. So, there's my box, it's 110 pounds. It's on the ramp, as we can see. And the ramp's at a 24-degree angle. Right? And the way ramps work is they take some of the weight off of the object that you're pushing up. Okay, so the weight itself is, part of it's going that way, and the rest of it's going that way, perpendicular. All right? So the 110 pounds is the weight caused by gravity, and gravity goes straight down. So if we start off with that, the vector representing the weight of the box itself, based on gravity, is a straight down vector. That's not good. Let's try again. Start, nothing in. There we go. Straight down vector. We're not going to have things floating away. All right. And that's going to be 110. All right. The two component forces that are going into that are the one that's perpendicular to the ramp and the one that's parallel to the ramp. Those are the two component forces that we get when we're dealing with ramps. And if we consider those two forces, one is perpendicular to the ramp itself, and the other one is parallel to the ramp. So obviously, if I were to draw this well, try to do a better job here. Really? That looks more perpendicular. We get a right angle down here. The other thing to get that's not quite as obvious, but it is going to be accurate, is this angle up in here is going to be the same as the angle of the ramp. You can take that one on faith if you want to, but that's what it is. Right. So the perpendicular force and the gravitational force are going to be at the same angle as the ramp. All right. And this is the, let's say, weight perpendicular, and this is going to be the one, I'm going to say W sub n. And we'll call this W sub p. I said perpendicular and parallel, they both start with P. The physicists in the world figured that out. Hey, we got to come up with a different word to represent perpendicular, and that word is normal. So the normal force, also known as the perpendicular force, so that's sub n normal, sub p parallel. All right, so they want to know the component of the force that's parallel to the ramp, and this is like the easiest thing in the world to do. This is a right triangle, and this is the opposite, and that's the hypotenuse of this 24-degree angle. All right. The component force itself is, these are scalar numbers. 110 is the actual scalar magnitude. We're looking for the scalar magnitude of this. It's just basic right triangle trigonometry, SOHCAHTOA. So since we're dealing with the opposite side down here and the hypotenuse that we know and the angle that we know, known angle, unknown side we want, and a known side we know, right? Using that information, I know sine of 24 degrees should equal the parallel force over the hypotenuse. Sine of 24 is known by my calculator. It's going to tell me too, because I can't keep secrets. 0.4067 over 1. Cross multiply, I get W sub P. What I'm looking for is equal to 0.4067 times 10 times 110. It comes out to 44.74 pounds. Again, if it was me pushing this box up this ramp, that's how much force I would have to push to get the box moving. Anything above that's going to make it move faster. All right, but again, it's a 110-pound box. We only have to put 44.5 pounds or so of pressure just to get it moving up. And that's kind of how ramps work again. The steeper the ramp, the bigger this number is going to be. So if you have like a 5-degree ramp, you know, sine of 5 is close to 0 times that. That's going to take a lot of the weight off. So that's, again, that's why you don't have to push as hard to get things up a ramp. That's how it works.
5-degree ring you're pushing it.
Say
So
so.
you can push it like
Wanted to know, like,
100
yeah,
110 sine of 5. About 10 pounds of force.
just have like 100 foot
Alright.
5 degree.
5-degree ring.